Hello everyone. Today we are going to be investigating the force due to gravity between two objects. So the objective for today is to be able to use mathematical thinking to calculate the force due to gravity between two objects. So first of all, let's look at gravity. Isaac Newton worked on his laws, and he figured out that those laws were very closely linked to what he was studying in terms of gravity. So what he figured out was that there are a few things that affect the pull of gravity, and that includes the mass and the distance. So the mass is directly proportionate to the strength of gravity. So if there's more mass, then the strength of gravity will go up, the strength of the force of gravity. And if the distance is increased, then that means that the force due to gravity will decrease. So that means that if you have, and this makes sense, if you have two planets, then if you have them close together, then their force due to gravity, F little g, is going to be very big compared to if you have two planets that are very far apart, then the force due to gravity will be smaller. Okay, so that just means that it's inversely proportional. In your reference table, this is the equation that we're using. It's F sub g, the force due to gravity, force, not acceleration, is equal to m1, so the mass of one object, times the mass of the second object divided by r squared. There is one other thing that's in the reference table, that's this constant, big G. Big G is the universal gravitational constant, and it is, you can think of it as a compensation factor to adjust the values so that they agree with real values. The value of big G is 6.67 times 10 to the minus 11th newtons meters squared per kilogram squared. You must include units for G, for big G, in your equations or in your inventory. Or you'll lose that point if it's a 2-point question on the Regents. Okay? This is on page 1 of your reference table. So it's listed for you. You don't have to remember it. Okay, so let's look at the graph for the force due to gravity. As we said, as the radius increases, so this is not actually radius. In the equation, it says Fg is equal to big G m1 m2 divided by r squared. This r is not radius. It's the distance between two objects. So you don't cut it in half. So as you can see, as the distance increases between them, the force, as the distance increases, the force decreases. So they're inversely related. Okay. So again, the force is going to increase when you have more mass. So then this is an inverse square law because it's r squared. So if you multiply the distance by 2, you are going to make the value 1/4, so 4x equals 1/16, and so on. So this is something that we are going to have to work with, the proportions. This is something we talked about a little bit in centripetal acceleration and centripetal force, and we're going to get very familiar with it for the force due to gravity. So we talked about this already. You're just seeing it a little bit differently. So then the gravity of an object such as the Earth is concentrated from the center of its mass. So anytime it gives you an object and you have a radius, it's going to be the radius, and if you're a distance away, it's going to be a radius plus this distance. So make sure to keep that in mind as well. But you can think of it as like a point source. So what would happen if the distance doubled or the mass doubled? So if the distance doubled, it's 2. That means that the force is going to be 1/4 less than the original. But if the mass doubled, then it's going to double the force. Where'd it go? Okay, so we can calculate the gravitational attraction between Chuck Norris and the Earth. So this is just going to be Fg is equal to big G times the mass of one times the mass of the other divided by r squared. So then it's 60 kilograms times 5.98 times 10 to the 24th kilograms. This is also kilograms. And then divide that by 6.37 times 10 to the 6th meters. And this is times 6.67 times 10 to the minus 11. Make sure you include the units here. Newtons. Let's see. Oops. Meters squared per kilogram squared, so that it cancels out. Yep. Okay, so then when you plug this in, this is something that you have to work with the calculator for. So we're going to practice this in class, but you need to make sure you can get this. Okay, so when you plug this in, the 6.67 times 10 to the minus 11th newtons meters squared divided by kilograms squared times 60 kilograms times 5.98 times 10 to the 24th kilograms, is here just to make it a little clearer, divided by, this whole thing divided by 6.37 times 10 to the 6 meters, and this quantity is squared. You will get 589.8 newtons. Now, what does this actually mean? This is the attraction of Earth on Chuck Norris, of a 60 kilogram person, really. So what that tells us is that there is a gravitational attraction between any two objects. There is a gravitational it's actually between all objects, but we usually deal with just two objects at a time to make it simpler. So that means that there is a gravitational attraction between you and your desk, between you and the person next to you, and how that strength is dependent on how close you are to the object and the masses of the two things. Now, there's one other thing. We have found the force of gravity another way. This is 589.8 newtons, and that is dealing with the gravitational attraction between the Earth and Chuck Norris. But what about F of G, the way we've been doing it, where it's equal to mass times little g? Well, it turns out that if you do that, 60 kilograms times 9.81 meters per second squared, you end up with 588.6. So you can find out the gravitational attraction, or the force due to gravity, using the big equation, or you can use this equation here for small objects. It just means that the radius doesn't really matter, the distance between the two objects. It doesn't matter when they are so close together. Now, you might ask why there's a difference here compared to here. There's not a big difference, but that's because the 9.81 meters per second squared, that's an average of the acceleration due to gravity at different parts of the Earth, depending on how close you are to the center of Earth. So anyway, this is how you find it. The masses are not always 60 kilograms and 5.98 times 10 to the 24th kilograms. Some of these masses are on your reference table for planets and the sun and things. So for planetary bodies, these are on reference table page 1. So please keep that in mind as well. If I can change the color. Okay? All right. So now we have to deal with ratios. This is something that comes up a lot in the force due to gravity, just this big equation, because they want you to practice dealing with looking at how things change when you're only changing one of the other things. So the equation we have is the force due to gravity is equal to big G m1 m2 divided by r squared. So you can pretend that you are comparing this first one, and the first one is 1. Nothing is changing, so everything is 1. G doesn't really matter. M1, M2, it's all 1. And then the second one, if the mass is doubled, so if each mass is doubled, it becomes G times 2m1, 2m2 divided by r squared. So it goes up by 4. Because you can then say this is, where did it go? FG1. So then FG2 is equal to 4 FG1. Okay? Now what about if the distance was doubled? It's the same idea. We can then plug in G M1 M2 and then divided by 2R, and this quantity is squared. So then you end up with 1/4 of FG1. So it is then quadruple, 1/4 less. So this first one, whoops. This first one, if you're changing the different masses by different amounts, it's going to be different. Like, it's not always going to be 1/4 or 4 times as much. You could change this mass by 2 and this mass by 3, and it changes the proportion. But that's how the ratios work.